Okay, so 7 here. Okay, so what are integrated rate laws? So for any chemical reaction, and I guess I could just go, so for any general chemical reaction, like this, where I've given our stoichiometric coefficients in lowercase letters here, and our actual constituent atoms. This is probably a bad idea, but so those are our coefficients. And that really doesn't want to do that. Okay. So those are our coefficients, and these would be our elements, or our compounds, or whatever our reactant species are. So reactants, what's I want to do here? Not elements. So these will be our reactant species, and these will be our product species. Okay. So for any reaction like this, assuming, or any bimolecular reaction like this, assuming that the rate only depends on the reactants and their concentrations, then we can write the rate law as K, which is just our rate constant, times concentration of A to the power A, concentration B to the power B. Now, if we wanted to know what the rate of change of our A species is, which is just dA by dt, then it's going to be equal to this rate. And so the integrated rate law could be found by integrating this expression. Now, this particular expression is going to be a little tricky and can't be done really super easily, but can be done in simpler cases. So if we consider a bimolecular, or the simplest bimolecular reaction, which is to say that we have two A's going to a B, right? So the same species itself to give you your B species, then our rate is just going to be Ka squared, and so then the minus sign here, I didn't mention it before, but the minus sign here is because we're lowering our concentration of A or consuming our concentration of A to produce B, so it's going to be a negative change in the concentration of A. Okay, and then we can, with our rate expression, we can rearrange it to make it a little nicer for integration. So minus dA over A squared is K dt. So now we can integrate this, right? So we're going to integrate this guy over time, and we're going to integrate this guy over A. going from some initial A concentration to some final A concentration. And I guess I'll leave these things in here. Okay? So when we integrate 1 over A squared, we can just use our typical integral or any derivative that everyone should remember, where you add 1 to your power and divide by it. Now, I'll rearrange this a little bit to make it more obvious. And I'm going to rearrange it as minus a to the minus 2. So recall that if it's in the denominator, then it's a negative power. Okay, and so I've just rearranged this side, but I'm going to leave that alone. So now, carrying this forward, doing this one first, this is just going to be kt from 0 to t, which when t equals 0, the whole thing's going to equal 0, so this just equals kt. And now carrying this one forward, this is going to be, so add 1, minus 2 goes to minus 1, and then divide by the power, so divide by minus 1. So then it's negative a to the minus 1 over minus 1 from a naught to a. I'll actually write it out side of the bracket in retrospect. Okay, and I'm just going to migrate these up. And so then we can arrive at our integrated rate expression as these two equal each other. And so this is going to equal, so that's, these minuses are going to cancel. And then it's just a minus 1, so it's a minus 1 minus a naught minus 1, so that's our initial concentration of species A in this case, is equal to KT, or as we want to solve for our A species, we could write this as 1 over A equals KT plus 1 over A naught. And then so this is our second order, in this very simple case, integrated rate law. All right, so just to wrap back up, so an integrated rate law is just relating your rate of reaction, to your rate expression, from which you can only get once you know your balanced equation, and then integrating it. And so it will be different depending on the reaction you look at. So if we check the solution here, in the solution we have an example for a first order expression, and if you solve the first order expression, you get what is shown here, which comes out to be a law relationship between the rate and your concentrations. And so comparing this to the first order rate expression, or the second order rate expression I derived, we see that they're different. But the steps you follow are basically the same, although much more complex reactions will require much more complicated math. So this solution is correct. as it correctly explains what an integrated rate law is. There.